Time is without question the most intimately familiar phenomenon in all of existence. You have been immersed in its passage for every single moment of your life. At this very instant, as your eyes scan these words and your mind processes their meaning, time continues its relentless march forward. Seconds dissolve into nothingness. The horizon of tomorrow continuously collapses into the immediacy of today, and the vividness of now perpetually recedes into the stillness of memory. You can feel this happening within you. You inhabit this temporal flow like a fish inhabits water. There is no escape from its grip. And yet, despite this overwhelming evidence of your senses, time does not actually exist. Not in the manner you have always assumed. Not as an intrinsic, non-negotiable component of physical reality. Not as the great cosmic river in which you imagine yourself gently floating. Not as the immutable stage upon which the grand drama of the cosmos unfolds. Within the most profound and accurate physical theories we currently possess, the frameworks that describe the universe at its most elemental stratum, time simply evaporates. It vanishes from the mathematical formulations. It becomes superfluous, an artifact no longer required. It may very well be, as Julian Barber has proposed in one of the most meticulous and intellectually formidable treatises ever composed on this topic, nothing more than a grand illusion, an illusion of staggering persistence, breathtaking conviction, and universal scope, but an illusion nevertheless. I recognize that statements of this nature often sound like philosophical musings or semantic gymnastics, or the kind of pretentious pronouncements people make at social gatherings to sound intellectually profound. This is not that. This is the inevitable conclusion you arrive at when you take seriously the two most successful physical theories ever devised by the human mind, general relativity and quantum mechanics, and attempt to fuse them into a unified, coherent portrait of existence. When you perform that fusion, time drops out of the picture entirely. The cosmos, as described by quantum gravity, is a cosmos devoid of time. Everything we associate with temporal progression, motion, causality, the distinction between before and after, the subjective sensation of flux, all of it demands explanation. These phenomena are not foundational features of reality, they are emergent properties, things that arise from a deeper, timeless substrate. Following 5 decades of intensive work at the intersection of quantum mechanics and general relativity, grappling with the profound mysteries of black holes, entropy, information theory, and the architecture of space-time, I have arrived at the conviction that this represents one of the most profound and yet most neglected truths in all of physics. Time does not exist. Allow me to demonstrate why this must be so. 2 theories, 1 catastrophic problem. Let us begin by examining the fundamental conflict that exposes this problem. General relativity stands as our master theory of space-time and gravitation. It articulates how matter and energy warp the geometry of a 4-dimensional continuum called space-time, and how this curvature subsequently dictates the motion of matter within it. This theory has survived every experimental test thrown at it with exquisite precision. From the detection of gravitational waves and the imaging of black holes to the observation of the universe's expansion, the bending of starlight around massive celestial bodies, and the necessary corrections built into global positioning systems. It works flawlessly. Within general relativity, time is woven into the very fabric of space-time. It constitutes one of the 4 dimensions. It is malleable, stretching and compressing in response to gravitational fields and relative velocities, but it undeniably exists. Every point in this 4-dimensional tapestry possesses a specific time coordinate. Events occur at defined space-time locations. Causality is embedded in the light cone structure that governs how information can propagate. Quantum mechanics, on the other hand, is our theory of matter at the most diminutive scales. It depicts particles not as tiny billiard balls, but as wave functions evolving against a fixed, unchanging background. This theory operates with a precision that borders on the supernatural. The anomalous magnetic moment of the electron has been predicted to an astounding 12 decimal places. It works impeccably. Within quantum mechanics, time functions as an external parameter, a laboratory clock ticking away uniformly in the background, furnishing the framework against which the Schrödinger equation guides the evolution of the quantum state. In standard quantum mechanics, time is not treated as an operator like position or momentum. It stands as a classical background variable, absolute, fixed, simply given. Now attempt to combine them. Endeavor to formulate a quantum theory of gravity, a theory where space-time itself becomes the quantum system under consideration, where the geometry of the entire cosmos is described by a wave function, and where there exists no fixed background to supply a time parameter. The difficulty that arises is immediate, catastrophic, and absolutely fundamental. Within general relativity, there exists no privileged time coordinate. Space-time exhibits covariance. All coordinate systems are equally valid, including every possible choice of time. Different ways of slicing the four-dimensional fabric into three-dimensional spatial surfaces at successive moments are all equally legitimate. There is no universal now. Within quantum mechanics, the Schrödinger equation mandates that the wave function evolves in time. Each dipso dt ka h psox. Time serves as the external parameter. Evolution is defined with respect to time. How then do you write the Schrödinger equation for the entire universe when there is no external time to be found? When time itself is part of what you are attempting to describe quantum mechanically? You cannot, at least not directly. The naive combination collapses into incoherence. The Wheeler-DeWitt equation and timelessness. During the 1960s, John Wheeler and Bryce DeWitt undertook the ambitious task of formulating the fundamental equation of quantum gravity. What emerged from their efforts was something both extraordinary and deeply unsettling. The Wheeler-DeWitt equation reads H0. The Hamiltonian operator acting upon the wave function of the universe yields 0. Observe carefully what is missing from this expression. There is no IH pes t on the right-hand side. There is no time derivative whatsoever. There is no time variable present at all. In ordinary quantum mechanics, the Schrödinger equation states that the Hamiltonian generates evolution through time, IH fois t fois h sids. The Hamiltonian tells you how the quantum state transforms as time progresses. In the Wheeler-DeWitt equation, the Hamiltonian acting on the universal wave function produces 0. The state does not change with time. It cannot change. There is no time with respect to which it could evolve. The wave function of the universe stands static, frozen, timeless. When Wheeler first confronted this result, legend has it that he wandered about murmuring, "Time has no meaning at the Planck scale." DeWitt found himself profoundly troubled by the implication. Both men recognized what the equation was declaring. At the most fundamental stratum of quantum gravity, time simply does not exist. The universe described by the Wheeler-DeWitt equation is a single static quantum state. No evolution, no before, no after. A wave function that assigns amplitudes to various three-dimensional geometries of space. But those geometries do not unfold in sequence. They exist simultaneously in quantum superposition. They do not evolve. They simply are. This stands as one of the most disturbing results in all of theoretical physics. And it is not some fringe speculation cooked up on the margins of respectability. It follows directly from taking general relativity and quantum mechanics seriously and attempting to combine them into a coherent whole. Where does time come from? If the fundamental equation of quantum gravity contains no time, then time must somehow emerge from something that is itself timeless. But how could this possibly occur? This conundrum is known as the problem of time in quantum gravity, and it has remained one of the central challenges confronting the field for the past 60 years. Here is the most developed answer we currently possess: relational time. This idea was originally proposed by DeWitt himself, and subsequently developed by many others, most influentially by Carlo Rovelli and Julian Barber. The crucial insight is this: we never measure time directly. What we actually measure is change. We measure correlations between physical systems. Consider carefully what a clock actually does. A clock is a physical system, a pendulum, a quartz crystal oscillator, a cesium atom that undergoes a periodic cycle. We measure time by counting those cycles and comparing other processes to them. When someone asks, "What time is it?" what they are really asking is, how many oscillations has this cesium atom completed since we last synchronized our references? Time is defined relationally through correlations between physical systems. In a timeless universe described by the Wheeler-DeWitt equation, there exists no external time, but correlations nevertheless exist between different degrees of freedom within the universal wave function. Certain degrees of freedom can serve the role of clocks. They correlate systematically with other degrees of freedom, creating an internal notion of before and after. The expansion of the universe itself functions as one such clock. When we state that something occurred 1 billion years after the Big Bang, what we actually mean is that it happened when the universe possessed a particular size, a particular density. Size stands in for time. This is relational time. Time is not a fundamental background. It is a relationship between physical systems. It emerges from correlations in the universal wave function. From the outside, from the God's eye perspective of the Wheeler-DeWitt equation, there is no time. There is only a static wave function. But from the inside, from the perspective of an observer who is herself an integral part of the universe, she experiences time as the correlation between her internal state, her memories, her clocks, her biological processes, and the other degrees of freedom surrounding her. Time is internal, relative, emergent, not fundamental. Julian Barber and Platonia. Allow me to tell you about Julian Barber, for he has contemplated this matter more carefully and more radically than perhaps anyone else. Barber is a British physicist who worked for decades as an independent researcher, supporting himself through translation work while pursuing what he was convinced was the deepest problem in physics, the nature of time. In his book, The End of Time, published in 1999, Barber argues that time is completely and absolutely absent from the fundamental description of reality. His framework envisions the universe at any moment as a configuration, a complete specification of where everything is located relative to everything else. He calls the space of all possible configurations Platonia. This is not a place in space or time. It is a mathematical space. Each point in Platonia represents a possible now, a complete snapshot of the entire universe. In Barber's picture, the universe is not a sequence of configurations evolving through time. Rather, it is a probability distribution over all configurations in Platonia. The wave function of the universe assigns amplitudes to different configurations. Some are more probable, some less so. The experience of time, the sensation of moving from one moment to the next, arises because high-amplitude configurations contain records of lower-amplitude configurations. The configurations that are most probable in Barber's framework are those that contain what he calls time capsules, internal structures that look like histories that encode apparent records of a past that seem to remember a sequence of events. You experience time because you are a configuration, a particular arrangement of matter, that contains detailed records of what appear to be earlier configurations. Your memories, the physical traces of past events embedded in your surroundings, the entropy gradient you observe, all of these are internal features of your current configuration, not records of something that actually happened sequentially. They are simply features of this configuration that happen to look like records. This is a radical proposition. It asserts that there is no past, there was no sequence. There are only configurations, some of which contain apparent records of a past that never actually occurred as a sequence. The past is an illusion encoded in the present configuration. I find this both fascinating and deeply uncomfortable, but my discomfort does not make it wrong. The thermodynamic arrow is not time. Let me now address the most powerful objection typically raised against the claim that time does not exist. But entropy increases. The second law of thermodynamics is demonstrably real. Eggs break and do not spontaneously unbreak. Causes invariably precede effects. The past is manifestly different from the future. Surely this proves that time is real? Yes, the thermodynamic arrow of time is real. The asymmetry between past and future is real. But, and this is the crucial distinction that must be grasped, the thermodynamic arrow is not the same thing as time itself. The thermodynamic arrow tells you about a gradient in entropy across configurations. Our universe began in a state of extraordinarily low entropy. It has been progressing toward higher entropy ever since that initial moment. This gradient, this systematic difference between low entropy configurations in one direction and high entropy configurations in the other, is what we call the arrow of time. But this gradient exists within a timeless structure. In Barber's language, among all configurations in Platonia, the high-amplitude ones are clustered in a way that exhibits systematic entropy variation. The configurations that are most probable form chains, sequences of configurations where entropy increases along the chain. An observer situated inside such a chain experiences entropy increasing. She calls that direction the future. She remembers lower entropy configurations because her own configuration contains encoded information about them. She calls those memories the past. But the chain itself does not evolve. It does not move through time. All configurations in the chain exist simultaneously in Platonia. The observer's experience of moving through them is an illusion created by the chain-like structure of high-amplitude configurations. The arrow of time is real. Time itself is not. This distinction between the experienced directionality of change and the existence of fundamental time represents the most important conceptual separation in the entire philosophy of physics. Almost everyone conflates them. They should not. General relativity already hints at timelessness. Even before quantum gravity entered the picture, general relativity was already suggesting that time might not be fundamental. Within general relativity, there exists no preferred time coordinate. Different observers in relative motion or situated in different gravitational fields measure different elapsed times. We accept this time dilation as real. It is measured daily in particle accelerators and must be accounted for in GPS systems. But there exists an even stronger version of this insight. In general relativity, the equations themselves, the Einstein field equations, can be rewritten in a manner that makes no reference to time whatsoever. This is the ADM formalism, developed by Richard Arnowit, Stanley Deezer, and Charles Misner in the 1960s. They demonstrated that general relativity can be recast as a Hamiltonian system where the Hamiltonian is a constraint that equals zero. This is precisely where the Wheeler-DeWitt equation originates, from that zero Hamiltonian. The zero Hamiltonian means there is no time evolution. The system is frozen. All the dynamics, everything that looks like change when you are inside the system, is actually relational. It consists of one variable changing relative to another, not change occurring within an external time. In general relativity, the universe is already a timeless structure in this sense. The appearance of time evolution is an artifact of how we choose to parameterize the solutions. Different parameterizations yield different times. The physics, the actual physical content, resides in the relationships between physical quantities, not in their evolution with respect to some external time parameter. Quantum mechanics reveals this timelessness more starkly, but general relativity was already pointing in that direction. Loop quantum gravity and spin foams. In loop quantum gravity, the most developed alternative to string theory for quantizing gravity, this timelessness is rendered completely explicit. In the spin foam formalism of loop quantum gravity, the universe is described by a mathematical structure called a spin foam. This is a kind of four-dimensional network, a graph of nodes connected by links with quantum numbers assigned to those links. There is no time within this structure. The spin foam represents a complete history of the universe, but it is not a history that unfolds in time. It is a static mathematical object, a four-dimensional structure, a complete specification of the quantum geometry of space-time. What we experience as temporal evolution is our reading of the spin foam from inside it. We occupy one small region of the spin foam, observing correlations between our local degrees of freedom and others. Those correlations generate our experience of a temporal sequence. But from the outside, from the perspective of the mathematical structure itself, there is no sequence. There is only the spin foam, static, complete, timeless. Carlo Rovelli, one of the founders of loop quantum gravity, has written beautifully about this subject. In his book, The Order of Time, he argues that time is not fundamental, that it emerges from thermodynamics and quantum correlations, that the fundamental laws of physics do not distinguish past from future and do not require a time variable. I do not agree with Rovelli on everything. We have had productive disagreements over the years. But on this central point, I believe he is correct. The fundamental description is timeless. Entropy and the birth of time. If time is not fundamental, then where does our experience of it come from? Why is it so vivid, so universal, so seemingly impossible to escape? The answer lies in entropy and the initial conditions of our universe. The universe began in a state of extremely low entropy. The Big Bang was a remarkably smooth, ordered, low-entropy initial configuration. Since that moment, entropy has been increasing. This entropy gradient creates the arrow of time that we experience. But more than that, it creates memory. Low entropy in the past and higher entropy in the present means that the present configuration contains records, traces, of the lower entropy past. Your memories exist because entropy has been increasing. Your brain, at higher entropy, contains encoded information about lower entropy past states. That is what memory is. And anticipation, your sense of an open, undetermined future, exists because you cannot have memories of the future. High entropy configurations do not contain records of even higher entropy configurations. The future is genuinely unknown because records do not flow backward along the entropy gradient. Thus, the experience of time is entirely a consequence of the entropy gradient. Given the entropy gradient, you will inevitably experience something that feels like time, a past that is known and fixed, a present that is current, a future that is open and unknown. But the entropy gradient is itself just a feature of the configuration we happen to inhabit. It is not fundamental time. It is entropy. The experience of time is the experience of being in a low entropy universe that is increasing toward high entropy. If we had started in a high entropy universe, if the Big Bang had been a maximal entropy configuration, there would be no entropy gradient, no memories, no arrow, no experience of time. Time as we experience it is borrowed from entropy. When the universe eventually reaches maximum entropy, the so-called heat death, entropy will stop increasing. The arrow of time will disappear. Not because time ends, but because the gradient that creates the experience of time will be gone. In a maximum entropy universe, there will be no before and after in the experiential sense, no causality as we understand it, no memory, no anticipation. Not because time ends, but because what we called time was always just entropy in disguise. Quantum mechanics and the now. Quantum mechanics adds another layer to the timelessness argument. In standard quantum mechanics, measurement collapses the wave function. Before measurement, the system exists in a superposition of possibilities. After measurement, it assumes a definite state. This collapse happens now, at a specific moment. But what exactly is now? In special relativity, simultaneity is relative. Different observers in different states of motion have different nows. There is no universal present moment. The tension between quantum mechanics and relativity creates a problem. If wave function collapse is instantaneous, if it happens now, and if now is different for different observers, then different observers would witness different collapses at different times. The physics would become observer-dependent in a way that seems inconsistent. Various resolutions have been proposed. The many worlds interpretation avoids this difficulty by denying that collapse ever occurs. The wave function never collapses. Every possible outcome happens in some branch of reality. There is no special now of collapse. There is only a timeless universal wave function and our experience of being situated in one particular branch. In the many worlds picture, time appears even more clearly as an emergent phenomenon. The universal wave function is timeless. It satisfies the Wheeler-DeWitt equation. Each branch corresponds to a sequence of configurations. Observers in each branch experience time as the correlation between their internal states and the configuration they currently inhabit. But there is no external time, no universal clock, no fact of the matter about which moment is now across all branches simultaneously. What doesn't exist when time doesn't exist. Let me be precise about what I mean when I say that time does not exist, for it is easy to misunderstand this claim. I am not saying that change does not happen. Change is real. Configurations differ from one another. Different regions of the universal wave function possess different properties. I am not saying that causality does not exist. Causal structure is built into space-time geometry. Events that are space-like separated cannot influence each other. Events within each other's light cones can. Causality is a geometric fact. I am not saying that memory is an illusion. Memory is a real physical phenomenon. Information encoded in current configurations about past configurations. I am not saying that the future is determined. Quantum mechanics introduces genuine randomness into the fabric of reality. The future is not fixed. What I am saying is that there is no external time flowing, no universal clock ticking, no background against which events occur sequentially, no fact independent of physical correlations about when something is happening. Time, in the sense of an absolute external fundamental parameter, the Newtonian sense, does not exist. What exists instead? Configurations, correlations between configurations, entropy gradients, causal structure, memory, and the experience of observers inside the quantum state who perceive these correlations as temporal sequence. This is the timeless universe, not a universe where nothing happens, but a universe where everything that happens is relational, internal, and emergent. Block universe, plus timelessness. I've spoken in another context about the block universe, the idea emerging from special relativity that all events in spacetime exist equally. Past, present, and future are all equally real, all equally part of the four-dimensional structure. The timelessness argument goes further than the block universe. The block universe says that all times exist equally. The present is not special. Past and future are as real as now. The timelessness argument says that time itself is not fundamental. The four-dimensional block is not a universe with four dimensions, including one time dimension. It is a mathematical structure with four dimensions, one of which we call time, because it has a special relationship with entropy. In the deepest picture, there is no spacetime. There are quantum states of geometry. Those states assign amplitudes to different configurations. In the high amplitude configurations, there are correlations that look like temporal sequences. We experience those correlations as time, but the underlying structure, the wave function, the spin foam, the mathematical object that truly exists, has no time in it. This is a further step beyond the block universe. The block universe is timeless in the sense that all moments are equally real, but it still possesses a time dimension, a direction in the four-dimensional structure that we identify with temporal experience. The Wheeler-DeWitt timelessness is more radical. Not even that structure is fundamental. It is emergent. It arises from something that has no time dimension at all. Rovelli's thermal time hypothesis. Here's one of the most creative ideas that has emerged from thinking about timeless physics. The thermal time hypothesis, proposed by Alain Connes and Carlo Rovelli. The idea draws from statistical mechanics, where there exists a special parameter associated with thermal equilibrium states. When a system exists in thermal equilibrium, there is a canonical mathematical structure, the KMS state, that defines a natural flow. This flow is generated by the modular Hamiltonian of the thermal state. Connes and Rovelli propose that this is what time actually is. Time is the thermal parameter associated with the thermal state of the universe. Not a fundamental feature of the equations, but a statistical feature of the quantum state. In a system far from thermal equilibrium, like our universe, which started in a very low entropy state, there exists a preferred thermal time that corresponds approximately to ordinary time as we experience it. In a system at thermal equilibrium, maximum entropy, the thermal time is still defined mathematically, but there is no experience of it because there are no thermal gradients, no correlations that register as memories or as temporal flow. This is beautiful. It ties together the statistical mechanical origin of time's arrow with the quantum gravitational timelessness. Time is what you measure with a clock, and a clock is a physical system that exploits thermal gradients to track its own evolution. Remove the thermal gradients and you remove time itself. I am not certain that this represents the complete answer. The thermal time hypothesis has its problems. It works cleanly in some contexts and becomes ambiguous in others. But it points in the right direction. It is the kind of idea that, even if wrong in detail, illuminates something true about the relationship between time and thermodynamics. Why we experience time so vividly. Here is what I consider the hardest question raised by timeless physics. If time does not fundamentally exist, why do I experience it so vividly? The present moment feels real in a way that nothing else does. The past feels gone and fixed. The future feels open and undetermined. The flow of time, second by second, moment by moment, is the most immediate datum of experience. More immediate than space, more immediate than matter, more immediate than anything else. How can this experience possibly be an illusion? Not some trick of perception, but the deepest truth I know. The answer, and I believe it is correct, though disturbing, is that your experience is exactly what you should expect from an information processing system embedded in a low-entropy universe with an entropy gradient. You are a configuration of matter, an extraordinarily complex one. Your brain processes information. It takes in sensory data, updates its model of the world, forms memories, generates predictions. All of this processing is physical. It occurs according to physical laws. Because your universe possesses an entropy gradient, your processing has a direction. Information flows from low entropy to high entropy. Your memories encode information about lower entropy past configurations. Your predictions are uncertain because higher entropy future configurations are many and varied. The experience of the present moment is the experience of your brain's current processing state, the state in which sensory information is being integrated, models are being updated, decisions are being made. The past is what has been processed and stored. The future is what has not yet been processed. The vividness of the present moment is a feature of your information processing. It is the moment of maximum relevance for your computational processes. Of course it feels vivid. It is where the action is, computationally speaking. And the flow of time, the sense of moving from moment to moment, is the experience of these processing states occurring in sequence. Each processing state is correlated with the next. The correlations create the phenomenology of flow. None of this requires fundamental time. All of it can be explained by entropy gradients and information processing in a timeless quantum state. What this means for physics, let me explain what the timelessness of fundamental physics means for how we actually do physics. First, we need to reformulate physics without time. General relativity already points in this direction with its diffeomorphism, invariance, and constraint Hamiltonian. Quantum gravity takes it further. The ultimate physical theory should not include time as a fundamental variable. It should describe static relationships between physical quantities, with time emerging as a derived concept. This represents a massive research program, partially accomplished, partially not. Second, the problem of time in quantum gravity is not solved. The Wheeler-DeWitt equation exists, but it is poorly defined and plagued by enormous technical difficulties. The loop quantum gravity spin foam approach is more rigorous but remains incomplete. String theory has its own approach through holography and ADS-CFT, where time in the bulk emerges from the timeless conformal field theory on the boundary. Each approach has its successes and failures. None is complete. The problem of time remains one of the deepest unsolved problems in all of physics. Third, our intuitions about time are not just unreliable, they are actively misleading. The progress that has been made on quantum gravity has come from people willing to follow the mathematics into deeply counterintuitive territory. Timelessness is counterintuitive. Accepting it, truly accepting it, requires abandoning something that feels like the most basic datum of experience. But physics is full of such demands. The earth moves, though it feels still. The sun does not rise, though it appears to. Time is relative, though it feels absolute. And now time does not fundamentally exist, though it feels more real than anything else. The universe does not owe us intuitiveness. The deep question. Let me conclude with the deepest question that timelessness raises. Not a physics question, a philosophical one, but one that physics forces upon us. If time does not fundamentally exist, if the flow of time is emergent from entropy gradients and relational correlations, if the present moment is a feature of information processing rather than a fundamental reality, then what is experience? What is consciousness, if not the thing that exists in the present moment, moving through time, accumulating memories, anticipating futures? The standard model of consciousness is deeply temporal. You are the thing that experiences time. Consciousness is the screen upon which the present moment appears. Remove time and you remove the stage upon which experience happens. But the physics says there is no stage. There is no external time for experience to occur within. There is only the static quantum state and the correlations within it, and the entropy gradient, and the information processing. Does experience itself exist? Is there a fact about what it is like to be you right now, in this moment, if there is no fundamental moment? I think the answer is yes. But it requires us to locate experience not in an external time, but in the correlations themselves. You experience what it is like to be this configuration, with these memories, with these sensory inputs, with this anticipation of a future. That experience is real. It is encoded in the configuration, but it is not happening at a time. It is simply a property of the configuration, of this particular point in Platonia, to use Barber's language, this particular node in the spin foam, this particular branch of the universal wave function. You are a timeless thing that contains the experience of time. Not a thing that exists in time, but a thing whose internal structure encodes temporal experience. This is strange. It is possibly the strangest conclusion in all of physics, and it is where the equations lead. Conclusion. Let me tell you what 50 years of thinking about quantum gravity has taught me about time. Time is not fundamental. The deepest equations we possess, the Wheeler-DeWitt equation, the spin foam formalism, the holographic principle, contain no fundamental time variable. Time is absent at the quantum gravitational level. What we call time is the experience of entropy gradients, relational correlations, and information processing in a universe that began in an extraordinarily low entropy state. It is real as an experience. It is real as a thermodynamic phenomenon. It is not real as a fundamental feature of the universe. This does not mean that nothing happens. Configurations exist. Correlations between configurations exist. Some configurations contain records of other configurations. Some physical processes are irreversible because of entropy. Causality is built into space-time geometry. All of this is real. What does not exist is the external clock, the background time, the universal now ticking forward, the river you imagine yourself floating in. That river is a cognitive construction, a feature of what it is like to be an information processing system embedded in an entropy gradient. It is your brain's way of organizing its experience of correlations. It is extraordinarily useful. It may be the most useful cognitive fiction in the universe, but it is not fundamental reality. Fundamental reality is timeless, static, a mathematical structure containing everything that is and was and will be all at once in a quantum superposition of configurations that we read from the inside as history. We are not beings who move through time. We are beings who contain the experience of time. And there is a profound difference between these two descriptions. That is what the physics says. And after 50 years of listening very carefully to what the physics says, I have learned to trust it, even when, especially when, it tells me something I find deeply uncomfortable. Time does not exist. And somehow, knowing that the moment I am in right now feels more extraordinary than it ever did before.